Cinematographers, gaffers, and lighting designers have for generations relied upon two basic tools for evaluating the intensity and quality of light: the light meter and the colorimeter, also known as the color temperature meter. However, since the development of solid-state lighting technologies, these devices have suddenly become unreliable. Traditional methods of measuring illumination are designed to calculate the characteristics of tungsten light, which has a predictable, continuous color spectrum. Conversely, light emitting from most solid-state fixtures has a profoundly discontinuous color spectrum. To accurately predict the behavior of modern lighting instruments, it's now necessary to measure the entire range and intensity of color that each type of lighting unit delivers. This measurement is called spectral power distribution. The tool one needs to take such measurements is called a spectroradiometer. Until recently, such devices were better suited to a laboratory environment rather than a movie set. Recently, however, a number of compact, portable spectral measuring instruments have come to market. To make proper evaluations of this color rendering interaction, we also need to apply the spectral sensitivity of the recording device. Spectral sensitivity data can be gathered in a number of different ways. Each method requires interference filtration, which diffracts the design illuminant source into separate wavelengths ranging from infrared to ultraviolet in nanometer-sized increments. The light transmitted through this filtration is recorded by the camera in question, and the results are measured and plotted on a graph like this one. Of course, the most reliable spectral sensitivity data is that which is published by the manufacturers themselves. Now, armed with both camera sensitivity readings and spectral power distribution data, we can plot the interface characteristics and see a bunch of numbers. Well, thankfully, there are color scientists at the Academy of Motion Picture Arts and Sciences. With their diligent effort, the Science and Technology Council has developed a computer program that crunches this data into both graphically useful information and profoundly demonstrative images. The program was modeled after an empirical test designed as part of the Esmeralda Laboratory, which is currently housed at the Pickford Center for Motion Picture Study in Hollywood, California. The test requires that a larger-than-typical Macbeth color checker be placed on a matte painting easel. In the foreground, a smaller chart composed of the exact same color samples is mounted onto another easel. However, this smaller chart has had the upper portion of each color sample cut away. The background Macbeth chart is illuminated with a tungsten light source. The foreground is illuminated with whichever light source is in question. When these two charts are precisely aligned and recorded with a camera, it effectively creates a split-screen image of each color tile. One can immediately see any profound differences in color rendering. Our newly developed computer program is able to accurately emulate this split-screen Macbeth effect, and in addition incorporates many other features to make it even more useful. It was immediately determined that this new tool, which we're calling the Academy Color Predictor, would be of great value to anyone who works with modern lighting devices, as well as being a very helpful and efficient device for those who design and build solid-state lights and their components. And so a team of code-writing experts have been called upon to develop the software that makes porting of this tool possible to many different platforms and operating systems. The end result is an open-source executable file that can turn almost any PDA or computer system into an accurate color rendering evaluation tool. A spectral power distribution measurement is recorded and uploaded into the program. This data can be immediately compared to the spectral power distribution of any other light source recorded in the program library, and their compatibility can be evaluated in correspondence with the spectral sensitivity data of whichever film stock or digital camera is selected. The comparison is easy to visualize because instead of mathematical formulae, we see color-accurate images showing the true look that would result from combining these light sources on set. Aside from the standard Macbeth chart, there are a number of other virtual test targets to choose among. For those who rely upon them, there is also an immediate listing of 3 different test metrics: CCT, CRI, and CQS, for whichever light source is chosen. There are added features that allow testing of things like the white balance, camera filtration, lighting filtration, and in addition, one can view some very sophisticated mathematical graphs in a 3-dimensional environment to help visualize the direction of color shifts that occur between the light sources being tested. This trilinear plotting feature is especially valuable for predicting whether post-production color correction can be relied upon for adjusting differences in color rendering between 2 test sources. In some cases, when the shifts are parallel, color correction will succeed admirably. However, When there's divergence in the direction of these shifts, color correction in a DI suite would be a costly and ineffective solution. One final feature will be an obvious benefit to those who design and build solid-state lighting units and their components. It enables one to create a virtual lighting unit, selecting any number in combination of emitters with an infinite capability of spectral power distribution, aiding in the potential to invent new lighting technologies with more accurate color rendering ability.